All right. Hello, class. Mr. Pettibone here. Hope you're doing well this afternoon. Sorry I'm a little bit late. I was in the shower and I was just enjoying the warm water and I lost track of time. Um, so, one other thing. I haven't posted the daily item for today yet. I'll post the daily item for today by 5 o'clock. Um, I forgot to. Usually I do it ahead of time, but I just forgot to. I'm getting a little bit of the end of the school year laziness happening for me right now, so I apologize. Um, hey Jackson. So I was foraging for like 5 hours yesterday, and I was trying to make some tongs, and I failed miserably at making tongs because the tongs that I have, they only work for holding something they're basically like scissors, right? So they only work if you are holding something thin. Like they can hold something thin just fine. But if you have something that's thicker, they just kind of go like that, and then the thing just rolls out. Um, and so after like 3 hours of foraging, I made this, which doesn't really look like very good tongs. But the problem was to make the tongs. It was like I needed the tongs, so I was trying to hold on to the thing while I'm hammering it, and I just couldn't hold on to it, and it would just fly off and land in the grass, and then the grass would light on fire, and it was just crazy. So I don't know. I might have to just buy some other tongs. I'll try like maybe one more time, and then I'm gonna give up. All right, so today I wanted to talk a little bit more about um, black holes and neutron stars. Okay? So, first of all, I wanted to talk about maybe neutron stars. So, as I said, neutron stars form when the star collapses and there's not enough there's not enough basically there's not enough pressure on the inside to prevent the collapse from happening, and the electrons get pushed into the protons and they form neutrons. Okay, so they're something that is the mass of the sun but the size of the earth of excuse me, not the size of the earth, they're like the size of a city. Okay, so they're incredibly small. um, so I wanted to. One of the things about neutron stars is that they spin incredibly fast, and I wanted to explain why they spin incredibly fast because we can actually explain it in terms of conservation of angular momentum. So, why do they spin so fast? Um, it's angular momentum conservation. L initial equals L final, where L is the okay. So the initial state is the state of the neutron star before it has collapsed into a neutron star, and then L final is after it has collapsed into a neutron star. Okay, so so there's a formula for angular momentum that I taught you, which is I times omega. Okay, and stars are approximately spherical, and there's a formula for the inertia of a formula for the inertia of a solid sphere is 2/5 mr squared. Okay, so I'm going to plug that into both sides. So we have 2/5 m r initial squared omega initial, and then 2/5 m r final squared omega final. So m initial and m final are the same, okay? Because it's the entire thing just collapses into the neutron star. So 2/5 m cancels out, and what I get is r initial squared over r final squared times omega initial equals omega final. Okay, which I can write a little bit better as r initial over r final quantity squared times omega initial. Okay, so we have this equation. All right. Now, for a neutron star, initially the star is the size of the sun, more or less. The sun is 10 to the 8th meters across. So our initial is approximately 10 to the 8th meters. Our final, okay, is going to be roughly the size of a city, which is maybe a kilometer or 10 kilometers across. Okay, so our final is let's say 10 to the 4th meters. So that means that our initial over our final would be 10 to the 8th divided by 10 to the 4th. So it's like approximately 10 to the 4th. And then if we square that, we get our initial squared over our final squared is like 10 to the 8th. So that's 10 million, okay? So what we find is that the final rotation rate of the neutron star is something like 10 million times the initial rotation rate, okay? So neutron stars are spinning crazy fast because of angular momentum conservation. So a typical star might take, of the order a week to do one rotation. And a neutron star is spinning multiple times per second. So, the surface of the neutron star is like almost going at the speed of light. So it's crazy. So I think that's interesting. Now, what if there is any sort of electric charge imbalance on the neutron star? So you might remember that when we talked about magnetism, the source of the magnetic field is electric current. So if there is any imbalance of charge on the neutron star at all, then that charge is going to be whipping around the neutron star several times per second. And it's going to create an incredible electric current, which is going to generate huge magnetic fields. So neutron stars have gigantic magnetic fields. They're like the most powerful magnetic fields in the universe, okay? Because they're spinning and it's possible for them to have charge imbalances. Michael Judson found a cool video to explain what's inside a neutron star. Maybe you could post a link. I believe they think that what is inside a neutron star is called a quark-gluon plasma, which is basically a state of matter that can only occur when you have incredible pressures, such as inside a neutron star. Okay, so that's a neutron star. The other thing I wanted to talk about, and so I'm going to circle back to black holes, but I want to talk about Jackson asks, are pulsars neutron stars, or are they a whole different thing? Pulsars are neutron stars. Yes, they're a special type of neutron star. So what you have with a pulsar is much like the Earth. So the Earth's magnetic field is not aligned with its spin axis. So you could have a neutron star that is its spin axis is like this, but its magnetic field axis is tilted with respect to the spin axis. So you have something like this. So the same thing is true of the Earth. So what happens is the magnet is going like this, okay? And if you have a moving magnet, it basically is acting like a transmitter for electromagnetic radiation. And so it's sending electromagnetic radiation out into space because of this offset. And so that's what we call a pulsar. A lot of it is just perspective. So you could have a neutron star, and if we're getting hit by the radiation from the neutron star, then we call it a pulsar. So it's just a matter of, kind of like the relative orientation. Okay. So I want to talk about the, I'm going to circle back to black holes, but first I want to talk about gravitational potential energy. And gravitational potential energy, we learned the formula U equals mgy. But it turns out that gravity, as we learned, this equation assumes that gravity is constant. The gravitational field is constant. But as we know, as you move further away from the surface of an astronomical body, the gravitational field decreases. So this equation only works near Earth. Or near an object where the gravitational field isn't changing very much. The real formula for gravitational potential energy is U equals minus G little m big M over R. So big M is the mass of the central body, and little m is the mass of the other thing, okay? And it has a negative sign, which is important. All right? Okay? So this is the real formula, okay? So let's suppose we had, for example, the Earth, okay? And what if we had a rock that is out here? It's really, really far away, okay? And the rock is going to beep, 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 fall and hit the Earth, okay? So the Earth has mass big M, the rock has mass little m. So this rock, it starts out basically infinitely far away, okay? All right, and we'll say that it starts out with basically zero speed. All right, so using this, I would like to figure out what is the speed of impact. Okay, what is the speed that the asteroid hits the Earth with? So we're going to use conservation of energy. So the initial energy when the asteroid is way out here is equal to the final energy, which is when the asteroid hits the surface of the Earth. We're going to assume that the surface has radius r. Okay? So the initial energy is basically kinetic plus potential. So it's minus big G, little m, big M over r. We said that r initial is infinity. Okay? Plus 1/2 little m v squared. But we said that the asteroid starts out with no speed. So this is the initial energy. The final energy is minus g little m big M over r because it ends on the surface of the planet. Okay? And then it has a certain amount of kinetic energy, which is the speed of impact. All right? So on the left-hand side, we actually have 0. Why? Because the kinetic energy is 0. And if you take, and r is basically infinity. So if you divide by anything by infinity, you get 0. So this, on the left-hand side, you have 0 plus 0. All right? So our equation is 0 equals 1/2 mv squared minus g little m big M over r. Okay? And so what we find is that the speed of impact is equal to square root of 2g big M over r. All right? So let's go ahead and do that calculation for Earth. Okay? So square root of 2 times 6.7 times 10 to the minus 11 times the mass of the Earth is 6 times 10 to the 24th kilograms over the radius of the Earth, which is 6 times 10 to the 6th meters. And we get roughly 11 kilometers per second. So quite fast. So what that means is if you were to take an asteroid that's really far away and drop it on Earth, it would hit Earth with a speed of 11 kilometers per second. Okay? All right. And that's assuming it has no speed. So actually, this is kind of interesting because if we think about asteroids hitting the Earth, which has happened throughout Earth's history, asteroids are basically rocks that are floating really far away, and then they come in and they gravitationally get pulled to the Earth, and they collide with the Earth. So what this says is that the minimum speed of impact, okay, the minimum speed of impact of an asteroid hitting the Earth is 11 kilometers per second, which is just crazy to think about, right? We could actually take this equation and turn it around, and we could say, well, what would happen if I threw something upward from Earth at 11 kilometers per second? If you did that, the thing would never come back down. Okay? So basically a rocket that's leaving the Earth has to achieve a speed of at least 11 kilometers per second, and once it does that, it'll leave Earth and never come back. Otherwise, it will eventually get pulled back to Earth. So for that reason, this is sometimes called the escape velocity. All right? So now what I would like to do is I would like to say, what if the escape velocity equals the speed of light? What if the escape velocity equals the speed of light? Then that means then nothing can escape. All right? Then nothing can escape. So let's go ahead and play around with the equations a little bit more. So we say, what if the escape velocity is the speed of light? Square root of 2 gm over r. Okay? So what that says is that r would then equal 2gm over c squared. Okay? So this is called the Schwarzschild radius. Okay? And if you have an object of mass m, okay, and you compress it so that its radius is less than this value, less than the Schwarzschild radius, then it will collapse into a black hole. Okay? Because a black hole, not even light can escape, and this is the radius that something has to have in order to have an escape velocity of the speed of light. Okay? So if it's smaller than that, then nothing can escape because nothing can go faster than the speed of light. Another thing that this equation says is that as the mass of a black hole increases, its radius goes up. So the more black holes eat, the bigger they get. Okay? Black holes that eat more are going to be larger. You might wonder, what do black holes eat? And black holes just eat random gas and dust that is floating around in outer space. So they eat mostly hydrogen that falls into the surface. So we could turn this equation around and keep playing around with the equation and say, what density does something have to have in order to become a black hole? And it's an incredibly large density. So if we think about a black hole, the black hole has some boundary, okay, where this is the Schwarzschild radius, call it r sub s, and if you cross this boundary, so if you are on one side of this boundary, you can escape. If you cross this boundary, then now in order to get back out of the black hole, you would have to exceed the speed of light. Okay? So once you cross that line, once you cross within one Schwarzschild radius of a black hole, you can never come back out. And so this is basically the black part of the black hole, okay? And this boundary that you can't cross is called, you can cross it, once you cross it, you can never come back. It's called the event horizon, okay? So anything that crosses the event horizon of a black hole, it can never come back out again. And then, as far as we know, within the event horizon, it's not a physical boundary. So actually, if you were to fall into the event horizon, nothing special happens when you cross the event horizon. It's only to external observers that are watching you cross the event horizon. Then it's just like, you disappear. So if you were falling into a black hole, you cross the event horizon, then you continue to the very center of the black hole, which is called the singularity. Okay? So really a black hole has a fairly simple structure. It's got an event horizon, it's got a singularity. If the black hole is spinning, then it also has another spot. It sort of has another boundary, which is called the ergosphere. And if you cross the ergosphere of a black hole, then you have to rotate with the black hole. Okay, so you can still get out, but if you're within the ergosphere, then you're going to rotate with the black hole, and it's like an ellipse around an ellipsoid around the black hole. Black holes also, black holes that are eating stuff, they're eating gas and dust. They also tend to have a what's called an accretion disk around them, which is basically all the matter that's spiraling around and into the black hole. And oftentimes, as material falls into the black hole, some of it gets ejected along the axis of the black hole. And so black holes are oftentimes accompanied by jets of high energy particles. So yeah. So Michael Judson asked, if black holes don't fuse, then what does the inside of the black hole look like? Well, black holes can fuse. If you take two black holes, actually a lot of work has gone into this. You need supercomputers to figure out what's going to happen. But if you have two black holes and you move them together, their event horizons actually will reach out and touch each other, and then they'll merge into a bigger black hole. And actually, it's interesting, the event horizon actually ripples after they merge. You can find videos of this online, the supercomputer simulations that people have done. But we really don't know. We really can't say for sure what is happening within the event horizon because no information escapes. We need data. If you've ever seen the movie Interstellar, they're talking about getting the quantum data from inside the black hole so they can solve the theory that they're trying to get. And that's the issue, is that if you want to see what's inside the black hole, you can do that, but you can't tell anyone else. It's like a secret. So really all we can do is sort of infer what's happening inside the black hole. So hopefully one day we'll be able to figure that out and maybe harness the power of the black hole. I, for one, think that would be awesome. All right, that's my lesson for today. I haven't posted the daily item yet. It'll be up by the end of the day, probably by 5 o'clock.